One thing I wanted to remind us of as we started lecture today is that the language of chemistry, the language of chemical reactions is moles. I gave you guys a version of this flowchart, and I'm expanding and adding one little bit to it. Remember that the flowchart I gave you actually put molarity here, but we found that it was better to use molarity as the conversion and have it give us volume. By the way, one thing I also wanted to say about these flowcharts is whatever conversion factors you have, those conversion factors can be acquired, if you don't have them, by taking the two pieces of information that it connects. So in those examples where you're solving for molarity, and you have the number of moles and you have the volume, you can't use molarity as a conversion factor. Instead, you use the two pieces of information to get the conversion factor. So that's another reason roadmaps can be helpful. If you know what you're going for, you know what pieces of information you need to get there. I'm adding one piece to it, which is the volume of gas. Because of that, I've actually changed how I wrote the other volume of an aqueous solution, because we looked at molarity being a conversion factor there. And now the volume of a gas. Technically, the best way to get there is by using Pivnert. N equals PV over RT. That's just a rearrangement of Pivnert. And we said that at STP, Pivnert solves for this conversion factor, 22.4 liters per mole. 1 mole will take up 22.4 liters of a gas, regardless of the identity of the gas. That's the volume that it will take up. So this is a new conversion factor that is useful if you're at STP. If you're not at STP, then you would need to use Pivnert to convert between moles of your gas and the volume of the gas. But in a similar way, you could also go, moles of the gas, and volume of the gas. You could also go from moles of the gas to the temperature or the pressure of the gas. This brings us to question 1 under the molar volume of gases. I want to solve this one with you guys. We're going to solve this on the board. So the question is, what volume of gas is produced when what volume of carbon dioxide gas is produced when 10 grams of methane reacts with oxygen? Notice that we have information about methane, and we want information about carbon dioxide. Sorry, Jacob. So that means we'll need to use a roadmap, and we'll need to convert between moles and moles. And because we're at STP, we can use this new molar volume conversion factor, 22.4 liters per mole. So let's look at where we're starting on the roadmap. Let's look at where we want to end up. We want to end up with the volume of carbon dioxide gas, but we're starting with 10 grams of methane. Let's say methane is A. That's information I have. That's where I'm starting. I'm starting at the mass of A. What's the only conversion I can do? Mass into moles. I'll need the molar mass of methane in order to do that. The language of chemical reactions is moles. Now that I'm talking about methane in moles rather than in mass, I can communicate about one species to the other. So I can convert now from moles of methane into moles of carbon dioxide. What do I need for that? The mole ratio. And the mole ratio comes from a little bit of different terminology. Is that what you're getting at? Our balanced chemical equation. So we'll need to write out the chemical equation. We'll need to balance it in order to get this. Now, which way do I want to go? Once I convert from moles of methane into moles of carbon dioxide, I want to go to the volume of carbon dioxide. And because this question is at STP, I can use the standard molar volume. The next problem that we're going to solve is not at STP, so I can't use that quick, easy molar volume. I'll have to use PivNert to convert between these. All right, let's write the chemical equation. Methane reacts with O2 to form CO2. To be honest, it doesn't matter what else I form technically, but I do need to have the other product so that I can balance it appropriately. What is the other product here? H2O. We make water as a product of combustion. If you need that time to be accounting for the atoms, do that. Don't shortchange yourself on how you balance a chemical reaction. I'm going to take us through it a little bit quicker so that we can solve this a little bit faster. 1 carbon on the left, 1 carbon on the right, 4 hydrogens on the left. I need a coefficient 2 in front of water to get 4 hydrogens on the right. That gives me 4 oxygens on the right, only 2 oxygens on the left. So a coefficient 2 in front of oxygen. Turns out the coefficients I added didn't even change carbon dioxide or methane, but I had to do it just to be sure. All right, now we set up a dimensional analysis. 10 grams of CH4. Conversion factor, grams of CH4 to moles of CH4. I don't want moles of CH4. I need to convert now into moles of CO2. Moles of CH4 goes on the bottom. Moles of CO2 goes on the top. I'm now in the species I want to communicate about, but I need to convert into its volume instead. Moles of CO2 on the bottom. Liters of CO2 on the top. Moles per liter, molar volume. Technically, this is written as liters per mole. Either way, flip it upside down, it works all the same. Do you guys remember why I've done this without any numbers? To make sure my units cancel. Don't get bogged down with the numbers until you know you've set up your conversions correctly. Because the numbers can change. Right now I could go in there and scrub out some of the numbers. But the conversions, the units, need to be set up appropriately. 1 mole of methane. Carly, do you know this one? 16. 12 plus 4. 16. Mole to mole ratio. Alina, do you know this one? Coefficient for methane, coefficient for carbon dioxide, 1 to 1. What do I put in for this molar volume of gas? Do I put the 22.4 on top or on bottom? I put it with liters. That was kind of a misdirection to say, do I put it on top or on bottom? Your answer should be put it with liters. 22.4 liters per 1 mole. Plug and chug. Tell me what you guys get. $14. Did you round to that? No. Oh, that's because I put the wrong molar mass when I did my conversion. Any decimal places? No. Oh. Those masses, like 10? Okay, so you rounded to 14.
No.
Oh, nice. Oops. Why do I keep putting grams? 14, and my units? Liters. And the identity, CO2. Okay, I want you to take a second, talk with the people around you. Without doing a calculation, can you determine how many liters of methane would be required to produce 14 liters of carbon dioxide? How many liters of methane to make that 14 liters of carbon dioxide? What do you think, Keon? 14. Hayden, what do you guys think? Yeah? Cole, what do you guys think? I don't think it's the same because the molar mass is different. Molar mass is different. I don't know if that would change. That's a good question. Does the molar mass of the gas change its volume? It doesn't. It changes its density. The molar mass of the gas will change the density of the gas, but not the volume it takes up at STP. So your answer should be 14 liters of carbon dioxide requires 14 liters of methane. That is to say, if we're dealing with gases in our reaction, then the coefficients in front of the balanced chemical equation can actually tell us moles. This can be read as 1 mole of methane reacts with 2 moles of carbon dioxide, or 1 mole of methane makes 1 mole of carbon dioxide. But if this reaction is being run at 1 temperature, 1 pressure, then you can also convert that into liters. 1 liter of methane reacts with 2 liters of oxygen. 1 liter of methane makes 1 liter of carbon dioxide. So the other thing that you could have done here is recognize that this conversion is 1-to-1. So just pulling this out and instead using the molar volume for for methane instead of carbon dioxide, you get the same exact number. Okay, so here's a new question. If 14 liters of CO2 is, if 14 liters of methane is needed to make 14 liters of carbon dioxide, how many liters of oxygen gas is needed to completely consume the 14 liters of methane? 28 or 7? A mole-to-mole conversion. For every 1 mole of methane, I need twice as many moles of oxygen. For every liter of methane, I need twice as many liters of oxygen. So if I'm using 14 liters of methane, then I need 28 liters of oxygen just to completely consume it. So it's a good idea here if I want complete combustion of methane and I don't want any methane unreacted, I should probably add more than 28 liters of oxygen. Make oxygen the excess reagent. And then real quick, how many liters of water vapor would this produce? Keon? 28. Because that's 2-to-2 or 1-to-1 with oxygen. So whatever volume of oxygen is also the volume of water. That's the idea of molar volumes with gases. If you're running this at one temperature and pressure, the language that you can use here is either moles or volume. All right, let's look at the problem underneath it. To be fair, you don't have the chemical equation. That makes this a little bit more challenging. But the question is, how many moles of sodium azide to make 75 liters of nitrogen gas at 25 degrees C and 1 atmosphere? The equation here is NaN3 decomposes into elemental sodium and nitrogen gas. By the way, this is how your airbag inflates. So if you get hit, there's a heating element in the airbag that quickly heats up the sodium azide to 300 degrees C, and then it decomposes and makes a bunch of nitrogen gas that inflates your airbag. Is this being run at STP? No. STP is what? What is the temperature, the standard temperature? 0 Celsius, or in Kelvin? 273.15. Standard pressure, 1 atmosphere. So we are at standard pressure, we're just not at standard temperature. So can I use molar volume 22.4 liters per mole? This only holds true at STP. So the incorrect way to solve this would be to say, I know the volume I want, I'll use molar volume to get to moles, and then from moles of nitrogen gas to moles of sodium azide, and from moles of sodium azide to the mass of sodium azide that I would need. But I can't use this volume, instead I'll need to use PivNert. And I can't use PivNert written like this, because that solves for moles. That is the version of PivNert I want. Okay, so I need to do a conversion that takes the volume of my sodium gas to the moles, the volume of my nitrogen gas to the moles of my nitrogen gas. Then I can do stoichiometry. So I'm going to do this in 2 parts. First, I'll use PivNert. By the way, I talked with Ryan Holcomb, who's the course lead for Gen Chem. He said he does not pronounce this PivNert. He pronounces it PVNert, which I don't like as much. I think PivNert makes a little bit more sense, but it turns out it's not unanimous across the scientific community. So I tried to teach you that. I will stand by it, to be honest. I'm going to rearrange this because I know the pressure of the nitrogen gas, I know the volume of the nitrogen gas, I know the temperature of the nitrogen gas, but I want to know the moles of nitrogen gas that I have so that I can start doing stoichiometry. N equals PV over RT. I've got pressure in atmospheres, 1 atm. I've got volume in liters, 75.0 liters. So which of my R values is useful in this equation? I've got one that has a number 0.08206 and one that has a number 8.314. Hayden? And can you tell me why?
Because for that one, you needed to have liters in atmosphere. That's the one.
Good. The other R value has units kilopascal liters. I want units of atmosphere liters. So that's how I choose my R value. And if you remember on your equation sheet for the final exam, you have that given to you, so you don't have to guess it. You don't have to put it on your cheat sheet. You just need to know where to find it. And my temperature, can I put in 25 degrees C? Because degrees Celsius will not cancel with Kelvin. So 25 degrees C plus 273.15, I get 298.15 Kelvin. I want to check first that all of my units cancel. Liters on the top, liters on the bottom. Atmosphere on top, atmosphere on bottom. In the bottom, I have Kelvin on top, Kelvin on bottom, which means I'm left with units of 1 over moles, or in other words, moles. So here's another plug and chug situation for us. Tell me what you guys get. Let's not do too much rounding. Let's do like 2 decimal places for this one. Units, identity, and 2, nitrogen gas. Remember, we're starting here. We know how much nitrogen gas we want to make, and we've just used PivNert to tell us how many moles of nitrogen gas that means we need to have. Now that I've done that part, I can go back to standard dimensional analysis. To be fair, you could have done this in your dimensional analysis. It's just really messy. So now I come back and I say 3.07 moles of N2. Convert moles of N2 into moles of sodium azide, Na, N3. Should we balance it? Yeah. Let's finish setting up the conversion and then, good idea, we'll balance it. The last step of my conversion, moles of sodium azide into grams of sodium azide. That's because that's what I'm trying to answer. How many grams of sodium azide do I want? I did get a little bit ahead of myself. I started doing all the conversions before I sat down to make sure that everything was balanced. This is a good place to check yourself. You've got moles of nitrogen, and you're about to do the mole-to-mole ratio. And the mole-to-mole ratio comes from the balanced chemical equation. Oh, shoot, I haven't looked to make sure that it's balanced. All right. Can anybody give me coefficients to balance this? 2, 2, 3. 2 moles of sodium azide makes 2 moles of sodium and 3 moles of nitrogen. 2 sodiums on the left, 6 hydrogens, sorry, 2 sodium on the left, 2 sodium on the right, 6 nitrogen on the left, 6 nitrogen on the right. Good work. So now the numbers that I plug into my mole-to-mole ratio, what do I put here? What goes on top, what goes on bottom? 2 over 3. Then we need to do a little bit of a calculator exercise with the periodic table. We'll calculate the mass of sodium azide. That's 14 times 3 plus 23. What do you guys get? 65 grams per mole. And now it's just a plug and chug calculation. When you guys are ready, tell me the grams that you get. Can you say it one more time for me? 133. Rounding to 3 sig figs. All right, let's just compare real quickly what we would have gotten if we mistakenly used the molar volume. 75 liters into moles divided by 22.5 gives me 3.34 moles of sodium gas. In actuality, I wanted 3.06 moles of sodium gas. The molar volume would have given me a higher predicted number of moles. Times 2 over 3 and times the molar mass, that would have made me think to put 145 grams of sodium azide, not 133. So the molar mass here, the molar volume, it's not happening at STP, so I can't use that nice molar volume conversion because it changes the amount of my materials I'm expecting. Okay. New topic for us. We're going to be moving to talk about Dalton's law. I appreciate Dalton for putting what the heck his law is into its name. The law of partial pressures. You guys ever tried to push something buoyant underwater? Push it down and then it pops back up. So you need more pressure to keep it down, so you and somebody else both lean down on it to push it down. Combined, your pressures add to a higher pressure. There's a total pressure on that buoyant thing going underwater. Some of it is from you, some of it is from your friend. That's all Dalton's law says. It says that in a mixture, the total pressure is equal to the sum of the individual pressures. Pressure total is equal to the pressure of A, the pressure of B, the pressure of C, so on and so forth. And because ideal gases all behave the same, it doesn't matter the identity of the gas, doesn't matter its molar mass, it simply matters how much of that gas is present. So in order to use Dalton's law, we need something called a mole fraction. This is often given the variable x sub n. N is just to tell us a specific element. So we can say x of hydrogen, H2, x of oxygen, O2, x of nitrogen, N2, the partial pressure of whatever we have. The mole fraction of x is the number of moles of your substance, N, divided by the number of moles total. In this case, N is kind of a bad variable for us because we're using it to represent different things. Here's another way that we can spell it out so it sounds a little bit easier. Moles of your specific substance divided by the total number of moles. This is very similar to something like percent mass. The mass of your solute divided by the mass of the solution, except we're not multiplying by 100, so it should always be some decimal place. This is always some number less than 1. The part over the total. In order to determine the pressure of N, we take the total pressure and we multiply it by the mole fraction of N. We say N makes up this much of the total, multiply that by the pressure, that's the pressure that N contributes. So in order to do any of this, we have to be able to find the total pressure, find the total number of moles, and find the moles of that individual component. Let's start by looking at problem 1 under this partial pressures heading. This one is asking for the partial pressure of each of the components. What is the partial pressure of hydrogen gas, helium, and neon at 35 degrees C? According to our equation, the pressure of any of the components is equal to the partial pressure, the total pressure times the mole fraction. And the mole fraction is the moles of that component divided by the total number of moles. Do I know the total pressure? We can figure it out. How could we figure out the total pressure? It's not given. But I do have other information. I have volume, I have temperature, and I have a number of moles. PV nert. So I'll take PV nert, PV equals nRT, and I'll rearrange it so that I can solve for pressure. That's nRT divided by volume. Now we're not told what pressure we need to be in, which means we can choose any pressure that we want to. We could use atmospheres, we could use kilopascals. That will change which R value we want to use. P total is equal to, well, which number of moles do I want to choose? I'll need to use all of the moles because they're all contributing to the volume, they're all contributing to the pressure. So this N, I'm going to have to sum each of those individual numbers. And by the way, these numbers are written just a little bit obnoxiously. It might be a little bit easier to see them like this. Notice that that last number is one order of magnitude smaller than the others. These all have units of moles. I just need to find the total number of moles. This is useful because I will need to find the total number of moles later on anyways. How many sig figs am I allowed to keep in this calculation? 3. How do I decide my number of sig figs from this calculation? Least number of decimal places. Well, this last number extends the furthest, which means these numbers decide my least number of decimal places. So I'm allowed to go to the tenths, hundredths, thousandths, tens of thousands, hundreds of thousands. What is that? The fifth decimal place. 1, 2, 3, 4, 5. I'm allowed to go to here. So I won't record 0.003800, just 0.00380. And I'm not actually even doing any rounding by that. I'm just chopping off the accurate number of decimal places. If I wanted to rewrite this, I could put 380 times 10 to the negative third moles. I know some people like working with scientific notation, other people despise it. So choose your own adventure there. Okay, that's what we plug in. P total equals 3.80 times 10 to the negative third moles. Anybody want to choose an R value constant for us? You want to use atmospheres? 0.08206 liter atmospheres per mole Kelvin. And then I put in 35 degrees C. You're right. 308.15 Kelvin. Divided by 10.0 liters. I know you guys see how obnoxious these units are and how long they extend, and I'm still going to encourage you to write them every single time, because the only way that you can check whether you've made a mistake or not is to look for the units. Moles on top, moles on bottom. Kelvin on top, Kelvin on bottom. Liters on top, liters on bottom. The only thing I'm left with is units of atmospheres on top. Can you guys tell me what you get here? Is it a large number or small? Small. Now that I know my total pressure, I can start solving for my partial pressures after I solve for my mole fractions. So let's look at the mole fraction for hydrogen. X for H2, 0.00250 moles of O2 over the total 0.0030 moles total. I didn't give you guys nearly enough space in this problem on the worksheet. True or false, this number must be less than 1. Yeah, it's called a fraction, a mole fraction. It needs to be less than 1. It is a part divided by a whole. Let's round this to 2 sig figs. Or I guess we could have done 3 sig figs, huh? 0.658. Why is there no unit? Moles and moles cancel. And it's a fraction. It is meant to be a ratio, not a unit. All right, now the pressure of H2 is 0.0096 atmospheres times the mole fraction of hydrogen, 0.658. We've already got a small pressure. Is it going to get larger or smaller? Smaller. What'd you get? 631. Units? Did you round to 2? Oh yeah, you would round to 2. 0.00632 atmospheres. That's how much hydrogen is contributing. Hydrogen contributes the most partial pressure because hydrogen constitutes the largest number of moles. All right, truth be told, there was another way to solve this. Instead of solving for the total pressure, I could have plugged in each individual number of moles and solved for their partial pressure right there. Whether that's more work or less work, maybe up to you. Probably less work. Now you know how to do it both ways. You know how to solve for the total pressure given a constituent of moles, and you know how to solve for the partial pressure. Why don't you guys take a couple more minutes and solve for the partial pressure of H2, I'm sorry, the partial pressure of helium and the partial pressure of neon. I'm happy to answer questions if you're confused about this calculation. All right, 30 more seconds to round out your calculations. Okay, if you didn't get to finishing them, let's finish them together. Can someone give me the mole fraction of the helium gas? 0.262. Let's keep it at 3 sig figs. Are you rounding it to 2 or 3? What do you guys get? 263? and the partial pressure of helium. 252 units, atmospheres. Anybody disagree? Mole fraction of neon. And the partial pressure of neon. I'm sorry, did I put that up there wrong? What'd you say? 0.07? Partial pressure. There's two ways that you can solve for that final part. You could do the calculation for the mole fraction based on the number of moles of neon divided by the total number of moles. Or you could just take the total number of moles minus the number of 1 minus the mole fraction of helium minus the mole fraction of hydrogen, and you're left with the remaining part. And then there's another way that you could solve for the partial pressure of neon. You can take the total pressure minus the partial pressure of hydrogen, the partial pressure of helium, and whatever is left is your final partial pressure. All right, good work. Problem number 2 talks about the situation when your partial pressure comes from water and a gas. Some of you that are in the lab course, this week you're doing an experiment where you are collecting a gas, but you're collecting that gas over the surface of a liquid. And so the gas that you collect, in this example number 2, we're collecting argon gas. But because I'm collecting this over the surface of water, there is some water that vaporizes and takes up space in that tube as well. So when we measure the pressure of the gas inside the tube, it's not just the pressure of the gas we collected, it's also the pressure of some water vapor that's sitting in there. This can be considered like a wet gas because it has water in it. And if we wanted to report a dry pressure, that is the total pressure of the system minus the pressure of water. You can see why we call it dry, because when you dry your clothes, you're getting rid of the water. When we subtract the partial pressure of water, we get a dry temperature. Those of you that go on to take organic chemistry, there's a technique in lab called drying that we use on organic liquids. You start with a liquid, you end with a liquid, but one of them we say is a wet liquid, the other is a dry liquid. And that's because in that process, you're pulling water out of the liquid, leaving you with a liquid that has no water, a dry organic solvent. So let's calculate for this one the pressure of just the argon gas that is collected over the water. What we're given is 2 liters of argon collected at a temperature of 26 degrees C and a pressure of 750 torr. What is the pressure of argon? And then it gives us the partial pressure of water at 26 degrees C is 25.2 torr. That's because at different temperatures, different amounts of water can evaporate. Higher temperature leads to more water evaporating, higher partial pressure of water. Lower temperature, less water evaporates, lower partial pressure. This problem has more information than you need. All we need to solve this problem is this equation. We're given volume, we're given temperature, we're given pressure. All of those variables would help me solve for the moles of argon, but I'm interested in the partial pressure of argon. So I take the total pressure, which is given, and I pull out the partial pressure of water, which is also given. The pressure of argon equals 750 torr minus 25.2 torr. There's a reason that I put more information than you needed in here. Because that happens. I want you to be aware that you'll be given word problems where there's more information than you need, and it can send you down a wild goose chase. If you started using all of that and plugging it into Pivnert, you'd find the only unknown variable is moles. What is moles going to do for you? Nothing. All right, what did you guys get when you plug this in? Can I report that as my final answer? What is the amount of significant figures I'm allowed in this? What operation determines sig figs? Subtraction determines sig figs, so I'm left with the tenths place. Here, I get to the tenths place. That's one decimal place, if you will. This has less decimal places. The decimal place is minus one decimal place. My last significant figure is at the tens place. This is the least number of significant figures. This one goes further. So I'm left at the tens place. Regardless of what my calculation is, I'm left at the tens place. Here's the tens place. That's what I'm left with. What answer should I report? 73? Sure, I could do 7.2 times 10 to the second, but I could also just write 720 atmospheres. 7.2 times 10 to the second atmospheres has the same number of sig figs. Alina. Oh, I'm sorry, thank you. Force of habit. Torr. What unit is torr equivalent to? Millimeters mercury is called torr. By the way, the pre-reading quiz has a confusing question on it. I haven't changed it for our section because I think most of you have already taken it, but I've changed it for future semesters. One of the questions says, which unit is equivalent to 760 torr at sea level? And the correct answer is 760 torr is 1 atmosphere. But the answer on the pre-reading quiz was millimeters mercury. That should have been worded as, what unit is equivalent to torr? Millimeters mercury. Not which is equivalent to 760 torr. That's atmosphere. All right, that's partial pressure. Let's take a break, get up, move around. We're going to come in and talk about kinetic molecular theory and diffusion and effusion before we leave today. 5-minute break, and then we're back in here. is that? You know, some students have like really small handwriting, and on their cheat sheets they'll put like the densest amount of words per line that they can. From this distance, I thought you had just a bunch of writing on a little slip of paper, and then you put it in your mouth. Yeah, well, for what? Eating a protein bar or for eating paper?
I could not do that anymore.
All right. Our last module in Unit 7 is on kinetic molecular theory. I just want to talk about those words. Kinetic molecular theory. What is it telling us about? Restate it. Expand its words. Just from the three words, kinetic molecular theory is a theory describing energy, motion, movement of molecules. Great. Kinetic molecular theory postulates, boy, that's a fun word, isn't it? Just means that they're assuming, you know what happens when you assume. We're only going to look at 5. we're looking at these postulates. 1, molecules have random movement. Oops. Or random motion. Gases are made up of small particles that are in constant motion, and they're changing direction only after collisions. You can kind of see that in this diagram. That if you watched any one molecule, you could actually see that its motion is predictable until it runs into something else. So let's watch this guy here. It moved a little bit this way. It ran into something and moved this way. And then it ran into something else and it started to move back. Now we can finally trace it moving to a different part of the screen. Random motion. If we traced this long enough, we'd see that its motion looks rather chaotic all over the place. And that's how it looks for all of them. These gases are made up of tiny particles, and those particles have random motion. Postulate number 2. The molecules take up no space. Another way of saying that is they have negligible volume. Remember how we said that 18 milliliters of water as a liquid expands into 22.4 liters of water as a gas. All of those same molecules could be compacted into 18 milliliters and not just expanded 1,000 times, but more than 1,000 times into 22.4 liters. So those gas molecules, they take up no space. Now this is actually showing them as taking up quite a bit of space. That's so that we can see it. But if we were actually looking at something this large, we would say that the volume we're looking at is very, very small. Postulate number 3 is that these molecules, by the way, do you guys know what these little dashes are? That's just to say I'm repeating the word above it so I don't have to rewrite molecules every time. The molecules exchange no forces. Another way of saying that is that they have elastic collisions. The forces that this postulate is talking about is something we're going to get into in Unit 5, in our last unit. It's talking about electromagnetic forces. The fact that these molecules have some sort of attraction and repulsion to one another. Remember at the start of the semester I passed around those magnets? Did I? I never brought them to you guys. I told you about them. Maybe when we get to Unit 5 I'll bring them in. They act like little magnets. They have attraction and sometimes they have repulsion. This theory states no, they don't. They can run into each other and then they bounce off, but they're not being pulled towards one another. They're not being pushed away by one another. They're not acting like magnets. They exchange no forces. Their collisions are elastic. Our fourth postulate the pressure comes from collisions with the container walls. Any of these collisions that you see between molecules is not contributing to the pressure of the gas. It's only when it runs into the walls of the container is it contributing a measurable volume, a measurable pressure. And our last postulate is that the average kinetic energy which we can say KE. Kinetic energy, like you guys mentioned, kinetic is talking about motion, movement. The energy of motion here is proportional to the temperature. Specifically, the temperature in Kelvin, not inherently the temperature in Celsius or Fahrenheit. There was a scientist named Maxwell and Boltzmann and the distribution that's named after them is actually what we're looking at here in this graph. They predict the distribution of energies of the molecules in a sample. On the bottom, on the x-axis, we say number of molecules. This is similar to anything you might see in a stats class, which is like looking at kind of a bell curve. The percentage of students that do this, the percentage or the number of students that score very high, the number of students that score very low, and right in the middle is the average number of students. And here we look at, oh, I have it backwards. I apologize. The number of molecules is here. As I was giving my example, I realized my axis was wrong as well. This is often the grade that you have in a class, a very high grade, a very low grade. And then you look at the number of students that have that grade, and you can look at a Bell distribution or any other statistics. This is just statistics of molecules. It says that the largest number of molecules in a sample will have an average speed. It doesn't look exactly like a bell curve. You can actually see that in blue here, it's a little bit lopsided to the left. Even with the red, it's a little bit lopsided to the left. There's two pieces of information on this graph that are a little bit interesting. At the top, you have the most probable speed. And this is often given VP, velocity that is most probable. That is to say, if you were to pick a molecule, what speed would that molecule have? Well, you have the highest probability of choosing a molecule at this speed because that is where most of the molecules or the largest number of molecules have that same speed. But there's another piece of information, and it lies actually out here to the right. This is the root mean square speed, also called URMS. The root mean square. If you take all of the speeds of the molecules in a sample and you square those speeds, and then you average all of those squared speeds, and then you take the root of all of those squared speeds, you would suspect that it would be the same as the average speed. But the average root mean square is actually a little bit higher than the average. That actually predicts this oblong tail. And so I think my graph is maybe not quite oblong enough. It's a bit lopsided to the left, a high steep on the left, and then a longer steep on the right, which is to say, it's not a perfect bell curve. It leans a little bit, it lingers a little bit on the right-hand side. And we'll use the root mean square calculation a couple of times. There's actually a lot of math. There's a lot of equations in here, like kinetic energy is equal to 1/2 mass times speed squared. I'm going to take us down to where it's a little bit more useful. So we get this equation, the root mean square speed. Speed there is being represented by what letter? U. U is representing speed. We're looking at the root mean square speed is equal to the square root of 3 times the gas constant times temperature divided by the molar mass. What a random equation. But it does tell us something. In green, I've given you the Maxwell-Boltzmann distribution for a specific chemical with a specific molar mass. So let's say that this molar mass is X. Now let's look at another chemical plotted on here with molar mass Y, which is smaller than X. How will the root mean square of this new chemical compare to this old chemical? If the molar mass is decreasing, then I divide these values, which are the same between the two, at the same temperature, using these constants. All I'm doing is changing the root mean square, or all I'm doing is changing the molar mass. Does the root mean square increase or decrease? I'm changing molar mass from green now to orange to be smaller. Is the root mean square going to increase or decrease? I'm dividing by a smaller number, so the root mean square increases. What would that look like on here? Well, the root mean square will be further to the right. You'll notice that the plot also flattens a little bit. As I increase to higher temperatures, I get a larger distribution of all kinetic energies, of all possible speeds. As I cool it, I get to a more uniform root mean square. All right, this is actually already being indicated. They're representing heavy element with blue and a lighter element with red. And we can see the Maxwell distribution leans more to the left for the heavy element and is flatter and leans more to the right for the lighter element. And also look at the molecules. Which molecules on average are moving faster? The red ones. Look at how chaotic their motion is. It's almost like you can track how the blue atoms are moving, but you can't track the red atoms. At a smaller molecular mass and the same temperature, remember, temperature is equal to kinetic energy. At the same temperature, they have the same kinetic energy. What is harder to move around? A small molecule or a small atom, or a big heavy molecule or heavy atom? A heavier one takes more energy to move around. These have the same temperature, but they'll have different kinetic energies. They'll have the same kinetic energy, they'll have different speeds. To take the same amount of kinetic energy and move a heavy thing means it's going to move slower. But that same amount of energy to move a light thing means it moves faster. We also said that kinetic energy is proportional to temperature, and we can control the temperature on this diagram. So can you make a prediction? As I cool this, will my graphs shift to the left or will my graphs shift to the right? To the left. As my temperature decreases, my root mean square will also decrease. These are actually the two big takeaways. As molar mass decreases, the root mean square decreases, and as the temperature decreases, the root mean square decreases. Oh, thank you. Yeah, that was incorrect. As molar mass decreases, root mean square increases. Thank you. All right, let's change the temperature on this thing. They've got a very cute way of controlling the temperature. As you press cold, ice comes up. And that ice pulls energy out of the molecules and slows their speed down. Look at how the Maxwell-Boltzmann distribution is changing on the left. The lighter massed molecule is still shifted more to the right than the heavier, but they're both shifting to a slower root mean square speed. Now let's see what happens when I heat this system up again. Increase temperature, I should increase the root mean square speed, which means my graphs should both start shifting to the right-hand side. And you'll notice the fire, it's actually making things that come near it a little bit hotter, and then that gets distributed into the other molecules. Oh, I blew the lid off. The movement that these atoms take can be referred to by their mean free path. That's how far a molecule moves before a collision. So I want to look at a couple of examples here. I'm going to pump some more particles back in here. Look at my pressure. My pressure is sitting at around 4.5, 4.8 atmospheres. And look at how long these molecules are able to move before a collision. If we trace this one, it's moving, has a collision. Moving, has a collision, has a collision, has a collision. Average out every molecule's movement before a collision, you get the mean free path. Do you think the mean free path increases or decreases when I change the pressure? And I can change pressure by one of two ways. I can heat this up. Pressure and temperature are proportional. I can turn up the temperature and I can turn up the pressure. Or I can add more particles in. More moles, more pressure. Those are proportional as well. As I add more moles or as I make these move faster, do you think the mean free path will increase or decrease? Raise your hand for increase. Raise your hand for decrease. And raise your hand if there's not enough information or you're not sure. All right, there were more hands for that it will decrease. So let's see what happens. Do you want to change the temperature or the number of moles? Let's change the temperature first, and then we can change the number of molecules. As they start moving around, and this is actually a little bit hard. We don't get to see the mean free path calculated. As they start moving around, they get more energy, which means they run into each other a lot faster. So the temperature kind of makes sense. They're moving faster, they're going to run into things faster. The other one is a lot more intuitive. As I increase the number of molecules in here, they're now competing against a lot of other molecules. So they're going to find another molecule a lot faster. As the pressure increases, the mean free path decreases. They have greater collisions at higher pressure, or they have more frequent collisions at higher pressure. All right, I actually wanted to take us back so we can calculate number one. We're going to do this one together. Calculate the root mean square speed of oxygen molecules compressed in a gas cylinder at 21 degrees C, 15.7 atmospheres. This equation, by the way, is given to you on your equations sheet. It's written down here on the bottom left. It says URMS is the square root of 3RT over the molar mass. The R value that I want, it is a gas constant, but I actually want kind of drastically different units. The biggest problem here is that the units that we need are not given to you on this sheet, which means this is something that you will need to know how to use for it to come up on the unit test or the final exam. You'll need to know these units. That might mean maybe just a section of your cheat sheet that has root mean square with this R value. The R value that we want is 8.314. That number should feel familiar. And then we want kilograms meters squared per second squared Kelvin mole squared. Moles. That informs us of what temperature we want. We don't want temperature in 21 degrees C, we want temperature in Kelvin. 21 plus 273, 294.15 Kelvin, divided by the molar mass. What is the molar mass of oxygen? O2 is 32 grams per mole. Do I want this in grams per mole? If I have it in grams per mole, kilograms and grams don't cancel. So I need to write this in kilograms per mole. Is it 32 kilograms per mole? The molar mass of oxygen is 0.032 kilograms per mole. Tricky. Kilograms cancels. Moles cancels. I have 1 over moles divided by 1 over moles. 1 over moles and 1 over moles cancels. I have Kelvin and 1 over Kelvin, so Kelvin cancels. What units am I left with? Somebody say that again. meters squared per second squared. Just based on how all of this turned out, I get meters squared per second squared. But all of this is also inside of a square root. So the way that I solved this was I did the calculation inside the square root first, and I got 229,271.54 meters squared per second squared. I did that all first so that I made sure I didn't get anything confusing with my calculator. Then I took the square root of that. So the root mean squared speed of oxygen molecules is 478 meters per second. I decided to round to 3 sig figs based on the pressure, although maybe I should have rounded to 2 based on the temperature, which would have given 480. All right. Good. Bit of a bulky equation. I do want to point out you can also solve for the molar mass of a compound if you're given its root mean square speed and its temperature. You have to do a little bit more algebra, but the molar mass, you have to square both sides. So that's the root mean square speed squared. You have to multiply this and then divide that, so you actually get 3RT over the square of the root mean square speed. But you can extract molar mass information from there. All right, this is what I actually meant to give us, which is that the mean free path feeds into diffusion. You guys understand diffusion intuitively. If you take, for instance, go to the airport and you get into a tram or a bus, everybody is highly concentrated. You can think of that as a lot of pressure. And then those doors open up and everybody diffuses from high pressure to low pressure. This is diffusion. Movement of molecules from high pressure region to a low pressure region. How can the mean free path explain diffusion from high pressure to low pressure? At high pressure, there's a very short mean free path. At low pressure, there's a very long mean free path. Which means inevitably, if a molecule gets bumped into and it gets shot towards low pressure, it's going to have a very long mean free path. It's not coming back. It's not going to run into anything that sends it back in the other direction. In fact, we saw this when we were looking at this diagram, and I blew the lid off of everything. Everything started to diffuse from that low pressure, from the high pressure inside to the low pressure outside. I'll open the lid up. The mean free path out here is incredibly high. They're not running into anything to send them back. Okay, I don't like biology because it's applied chemistry in an incredibly scary scale. And when biologists talk to me about diffusion of oxygen into your blood, they're like, oh, it just moves from high pressure to low pressure. It doesn't know. Oxygen does not know that it's moving from a region of high pressure to low pressure. Oxygen is just getting bumped around. And statistically, it has a good chance of getting pushed towards a region where there are less oxygen molecules, because it's getting hit on by other molecules where it's at high pressure and it's getting pushed to where there's a larger mean free path where there are less molecules. So when you think about breathing in and your oxygen is diffusing into your blood, it's not that your oxygen is drawn anywhere inherently. It just has a good probability of making it there. Talk about partial pressures. Nitrogen is also in your blood at a higher partial pressure than oxygen because there's a larger chance of nitrogen getting pushed around because there's more nitrogen getting pushed around. But nitrogen is inert, so it gets into your blood, it gets out of your blood. It doesn't do anything while it's in there. Oxygen, less inert, reacts, whatever, the whole Krebs cycle, mitochondria is the powerhouse of the cell stuff. You get it. Notice the mean free path, now that basically everything has evacuated and the pressure is much lower, everything gets to move around a lot more before it runs into a collision. Mean free path increases as pressure decreases. We measure the rate of diffusion, how quickly something moves away, with this equation. Rate diffusion. I'm putting diffusion as a subscript there. That's the amount of gas that's moving through an area divided by the unit of time. So we can say the rate of diffusion is 600 billion molecules per second, which is a very small number of molecules. Or we could say the rate of diffusion is maybe molar per molecule or per second. We're saying that it has a concentration change per second. And there are factors that change this. The concentration gradient. How concentrated is one region versus the other? That's going to change the rate of diffusion. How large is the area? How far does it need to travel? All of those things impact the diffusion, but they're a little bit trickier to apply. One thing about the rate of diffusion, do you guys see what molecules are left? What type of molecules are left in my system? Just heavy. All right, now to be fair, I may not have done a good job of having an even number of heavy and light atoms. So let's try and get this exactly right. And let's get them mixed around a little bit, give them some energy. And then I'm going to take the lid off again, and we're going to see if both of these compounds, these chemicals, diffuse at the same rate. I'll let them get mixed up for a little bit. In the meantime, let's define something similar to diffusion. This is effusion. This is movement through a small hole. It's terrible that they named it so similar. All right, what I'm going to do is I'm actually going to open this up to not be the entire lid off, but to be just a small hole, so that it's more similar to effusion than diffusion. But these two processes are very similar. Graham's law of effusion says that the rate of effusion is proportional to 1 over the square root of the molar mass. As molar mass increases, the rate of effusion decreases. As molar mass gets larger, I divide 1 by a larger number, which means my rate decreases. That is to say, heavy things effuse less quickly than lighter things. The process of a helium balloon deflating, we've all had a helium balloon that we've taken home and left in the ceiling of the room until it falls down. The helium inside the balloon is effusing through the small holes that make up the material of the balloon. But if the helium inside can effuse out, then the air on the outside should be able to effuse in. So why isn't the balloon stays at a constant volume and maybe just falls to the ground because it gets more dense? Instead, we all know that the balloon deflates. That's because helium is very, very light compared to the makeup of the air, nitrogen, oxygen predominantly. So the helium effuses out of the balloon. The nitrogen and oxygen can't effuse in at the same rate. I had the same exact number of particles, light and heavy. Which one has escaped faster? Light. The rate of effusion of the lighter things is higher than the rate of effusion of the heavier things. You can credit that to their root mean square speed. The lighter things are just moving faster. They're going to bounce around further. They're going to get out of that small hole quicker. And we can actually write this new law, which says the rate of effusion of A as a ratio to the rate of effusion of B is equal to the ratio of the molar mass of B over the molar mass of A. I want to point out the relationship. A on top to A on bottom, B on bottom to B on top, an inverse relationship. This is another equation that you have. On the bottom, rate of effusion, amount of gas passing through divided by the rate of time. On the top, rate of effusion of A over the rate of effusion of B equal to the square root of B over the square root of A molar mass. These are all equations that you have. You don't need to memorize them. You just need to know where they are and when to use them. So let's look at the problems that I gave you, because I have one last thing to tell you about, and then I might be uploading a solution to this worksheet rather than being able to get through all of them with you. Calculate the ratio of the rate of effusion of hydrogen gas to oxygen gas. So the rate effusion of H2 to the rate effusion of O2 is equal to what goes on the top? Square root of 32 over the square root of 2. I made the silliest mistake when I did this on my sheet, and I said the square root of 1 on the bottom. Hydrogen gas is H2. That's a silly mistake. I can put units in, but the units cancel. Grams per mole over grams per mole. Square root of 32 divided by the square root of 2 gives you 4. What is that saying? It says hydrogen gas effuses 4 times faster than oxygen gas. Good. That is, the rate of effusion of hydrogen is 4 to 1 with the rate of effusion of oxygen. The second problem gives us something different. It says an unknown gas diffuses at 18 milliliters per second. The same conditions of temperature, carbon monoxide diffuses at 14.1 milliliters per second. What is the molar mass of the unknown gas? I'm only going to have time to set this up. So I'm going to put the rate effusion of X over the rate effusion of carbon monoxide is equal to the square root of carbon monoxide. That's 12 plus 16, 28 grams per mole, over the square root of the molar mass of X. Could I have set this problem up a little bit better? I get to decide which rate goes on top, which molar mass goes on top. I should have written this differently. I should have written the rate of CO on top and the rate of X on bottom. Why? Because now I get the molar mass of my unknown on top and the molar mass of carbon monoxide on bottom. And I don't need to do all this algebra moving around the molar mass of my unknown. So this is 28, the square root of 28 times the rate of carbon monoxide, 14.1, over the rate of the unknown, 18.0. Units all cancel. Gives me the square root of the molar mass of my unknown. So I'm not finished, right? If I wanted to perfect this, I would say the molar mass of my unknown is equal to this whole setup squared. Right? Okay. I am just barely going to have enough time to put this equation on the board. It's this is deviating from ideal gases. We said that ideal gases have to follow specific laws. That was the kinetic molecular theory. A non-ideal gas is at too low of a temperature or too high of a pressure to avoid exchanging forces with other molecules. At too low of a temperature, electromagnetic forces come into play. At too high of a pressure, electromagnetic forces come into play. And so there was a man that derived an equation to correct for this. The van der Waals equation corrects for intermolecular attractions and intermolecular repulsions. Instead of Pivnert, we now have an equation that says the pressure plus this constant A times the number of moles squared over the volume squared, multiplied by the volume minus the number of moles times this constant B, is equal to nRT. It's no longer Pivnert, it's pressure plus this factor times the volume minus this factor equals nRT. This equation will not be on the unit test. This equation will not be on the final exam. This equation will be on Real Chem. And they will give you these values. A corrects for forces between molecules, and B corrects for the volume. They are different depending on the gas. Water has different A and B values. Hydrogen has different A and B values. I'm going to show you guys how to solve problem 4, which uses the van der Waals equation. I'll do that in a video, and I'll upload it to Canvas and to YouTube. And I'll give you guys an announcement letting you know that I've posted that video so that you can see how to solve it, because you will need to do it for the real chem homework. But the nice thing is that equation is not on your equations sheet because it's not coming up on your assessments. All right, thank you guys for your time. Next week, Unit 8. And we're going to have a lot to cover. So come prepared so that you have questions in mind so that we can knock down all those questions as we go. Have a good weekend. See you guys on Monday.
Are you not teaching Gen Chem 2 next semester?
I am not teaching Gen Chem 2. Yeah. Wes Sanders and all of our other faculty do a great job teaching that section, though.